So the next test we're going to talk about is the integral test. And the integral test basically says that if the sum of some sequence from n equals to, I guess let's say 1 to infinity. So say you have some series, I guess we'll use one we already know. So let's use a p-series. We'll use a p-series of 1 over n squared. And we do know that this converges by the p-series. But some other tests, such as the integral test, will also tell us this. And what the integral test basically says is, well, so imagine you have a series, and this series is actually, there's a bunch of discrete values, right? So when n is 1, this is 1. And then when n is 2, this is like half of that. Half is actually like a quarter. Okay, well, I'll try to draw this more to scale. And then when n is 3, this is like an eighth, and so on. So these are discrete values, and this is what our series is, right? We're adding discrete values to each other. And now instead of adding discrete values, we can by, I guess, taking the left-hand corner or the right-hand corner, it doesn't particularly matter, and creating a function with it. Whoa, that was okay. This is not a great function. Let's not judge my drawing skills. And what we know is that, so the area in blue is the area in blue is the value of our series, whereas the area in black is the value of the area of the curve under our function. And what this integral test basically says is that if, and this is an if and only if statement, if the integral from 1, so because we started our index at 1, to infinity, because we're going up to infinity, of 1 over x dx of 1 over x squared. So we have 1 over n squared, so we replace our n with x. And the reason we do this is because our n's are discrete counters. So it is vaguely important to make this change. If our series converges, then our improper integral must also converge. And if our improper integral converges, our series must also converge. So alternatively, if our series diverges, our improper integral must diverge. And if our improper integral diverges, our series must diverge. So this is a two-way street, if you will, where if you know the behavior of one, you know the behavior of the other. That is not to say that the sum of 1 over n squared is not equal to the integral of 1 over x squared. And this can be very clearly seen in this graph, right? It very clearly looks like the blue rectangles are consistently larger than my black integral function. And so we can comment on the behavior of what's going on, but we still have no idea what actually sum up to, what the series actually sums up to. But this test is very useful, actually, because then, so say I didn't know about the p-test. So I would go and integrate this, and I would find that this is equal to negative x negative 1, so negative 1 over x, got it. Negative 1 over x, we're counting from 1 to infinity, which gives me negative, so this is not the proper notation. Let's go back to our proper notation, let's call it a. Limit as a goes to infinity, so we'd have negative 1 over So we'd have equals the limit as a goes to infinity of negative 1 over a minus negative 1 over 1. And we find, so as a goes to infinity, negative 1 over a goes to 0. 0 minus negative 1 is equal to 1. And so gives us a finite number, which means the integral converges, and that also means that the series converges. We're just going to do one more integral test to show, I guess, prove in a different way that the harmonic series diverges. So let's say we have the harmonic series of 1 over n from n equals 1 to infinity. Notice I don't start from 0, because if I start from 0, then I've already broken my my series before I even started, because 1 over 0 is undefined. So we know that if the integral of 1 to infinity of 1 over x dx, if this converges, this will also converge. And if this diverges, this will also diverge. And so we know that this is equal to ln of x from 1 to infinity. Or let's limit as a goes to infinity of ln of x of 1 over 1 to a. This equals to ln of a minus ln of 1. Ln of 1 does equal to 0. So this as a goes to infinity of ln a. And ln a, so regardless of how slow ln a is increasing, ln a actually does indeed grow unbounded, which means that this is a diverging, I'm not sure if I spelled that right, but this is a diverging integral. So this improper integral does diverge, which means we know that our series alternatively also diverges.